get into this equilibrium more. So the way in which we quantify equilibrium is through the equilibrium constant and the equilibrium expression. Okay, so here I've got a generic reaction written where my big capital letters represent my, I'll say, chemical identity. So in other words, that could be like, my chemical symbol, right? CO2 or H2O or sodium chloride or whatever, right? My lowercase letter in this generic reaction is the stoichiometric coefficient, okay? So that's our balancing coefficient, okay? And notice here we've got the equilibrium arrow, forward reaction, reverse reaction. So now this equation right here is our equilibrium expression, which is also known as the law of mass action. Okay, so our big capital K, we're going to get used to seeing big K. That is our equilibrium constant. And the C right here stands for concentration. So C, I know we want to think maybe it stands for constant, but here C stands for concentration. Because as we shall see, we can think of equilibrium in terms of concentration in mole per liter or in terms of pressure for gas phase reactions. Okay, so now what does all this stuff mean? Well, once again here, the big capital letter, that's my chemical identity, same as the way I've written this reaction. Okay, so I'll write chemical ID for just chemical identity. Okay, so now what is this lowercase letter? Well, once again, it's the same thing. It's the stoichiometric coefficient. And in our balanced reaction, when we write the equilibrium expression, you might notice here that we're writing it as products divided by reactants. Okay, and the products are multiplied, the reactants are multiplied, products on top, reactants on bottom, and we take that balanced stoichiometric coefficient and we raise it to the power, okay? So now finally, these brackets right here, so this is something really important to note. Brackets mean molarity. So anytime we see something in a bracket, we mean its concentration is in units of mole per liter. Okay, so for example, we were talking about this reaction right here, this forward and reverse reaction, H2O plus CO is in equilibrium with H2 plus CO2. Well, let's write that with the law of mass action. Okay, so we can write the equilibrium constant, Kc, and each reaction will have its own unique constant. You don't have to memorize that number. We're going to learn how to calculate it. Okay. And it's also condition specific. All right. So we're not memorizing equilibrium constants. Rather, we determine equilibrium constants from data. Okay. So how would I write the equilibrium expression for this reaction? Well, I said, products on top. So we would say bracket, chemical identity, H2. We can see that this is balanced with a coefficient of 1. So we could put a 1 right there, right? Like raise it to the 1 power. But we don't need to do that, right? We know that anything raised to the 1 power is just itself, okay? So now that's going to be times CO2, okay? So products divided by reactants. And now that's H2O times CO, okay? And the way in which we determine this equilibrium constant is by plugging in these concentrations into this expression. We'll get lots of practice with this, okay? So let's keep talking about this slide right here. So the equilibrium position, that's what we call the set of equilibrium concentrations, okay? And so we will often refer to the reactants as the left-hand side of the reaction and the products as the right-hand side. And we move away from this traditional reactant product in equilibrium because we recognize the reactants can both function as reactants and products, and the products can function both as products and reactants, right? Because we have forward and reverse reactions. So we like to think of these this equilibrium position as either on the left or on the right. Okay. So what does all that mean? And so, oops, you notice I wrote KEQ. That's an older nomenclature. I'm going to write KC and KC, okay? So what happens if KC is much, much greater than 1? Well, if we think about this, because we know that it is products over reactants, or really like the right-hand side over the left-hand side, right? When K is much greater than 1, that means there's more of these products than there are reactants. So we would say the equilibrium position is on the right. Okay? So in other words, once this reaction stops evolving in time and the concentrations have equalized, right? The concentrations are constant with time. Equilibrium's been achieved. If the equilibrium constant's much, much greater than 1, then that means we've made more products than reactants. So we can say, and I'll put that in quotes as well, products are favored. Okay? Well, what if the equilibrium constant is much, much less than 1? Well, once again, because it's, products over reactants, when the equilibrium constant is much, much less than 1, we have more of these reactants at equilibrium than we do products. So that means our equilibrium position is on the left. Or another way we could say that is reactants are favored once equilibrium has been achieved. Okay, so I'm going to zoom ahead. I'm going to skip one slide. I did these out of order. Apologies. And I want to talk about a couple of these interesting examples. So first of all, let's write the equilibrium expression for both of these reactions. Okay, so this is H2 plus O2 to make 2H2O. So, and if you know your chemistry, you'll recognize this is an explosion. This is a combustion reaction. Hydrogen reacting with oxygen, right? That's definitely a combustion. So if I were to go to write the equilibrium expression, Kc, okay, products in brackets, which is H2O, and look, now I've got a coefficient right there. So I'm going to raise that to the 2 power, H2O squared, all right, divided by H2 squared times O2. And you can see the equilibrium constant for this reaction is 3 times 10 to the 81. All right, well, let's do this other reaction, okay? So Kc for this reaction now. So we've got CO on the right-hand side, and there's a balanced stoichiometric coefficient of 2, so we're going to say CO squared times O2, all divided by CO2. And you notice here that that all equals about 3 times 10 to the minus 91. So you notice there's 2 extremes that I'm showing here. This K is obviously much, 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 much greater than 1. And this K is quite clearly much, much less than 1. So, but what about these numbers? Are those reasonable numbers for equilibrium? And as it turns out, no. These numbers are totally stupid, ridiculous. 3 times 10 to the 81 is so stupid big that this reaction is not an equilibrium reaction, okay? I'm going to get a big, fat, thick arrow and say this reaction definitely proceeds all the way to the right because of the crazy, ridiculous magnitude of that equilibrium constant. And we don't think of combustion reactions as equilibrium reactions. Combustion reactions are not equilibrium reactions, okay? So now What about this reaction? So you notice here it says CO2 in the forward reaction will break up into 2 carbon monoxides and oxygen. And you can see this is 10 to the minus 91. That's also a ridiculously small, stupid number. And that number is so small that this equilibrium position is way on the left. So in other words, it's not an equilibrium reaction at all. In other words, CO2, if we just had only CO2, this crazy, stupid small number tells us there is no way CO2 is just gonna react and fall apart into 2 COs and 1 O2. It ain't gonna happen. CO2 is extremely stable, so it's not just gonna spontaneously do this forward reaction. However, if we had some carbon monoxide and oxygen, right, those two things will undoubtedly react to form CO2. Okay, so we can think of these equilibrium constants both forward and reverse. Similarly here, right, with this reaction, if I start with H2O, it is not going to spontaneously go backwards into H2 and O2. All right, H2O is stable, and it's just not going to go backwards unless we do something to it. Similar to CO2. In this case, CO2 is not going to go forwards in this reaction unless we do something to it. All right. So that's what we mean by the equilibrium position. Okay.